friends, in our previous sessions we were discussing about how we are going to use three very important concepts for revenue maximization, and we also discussed that there can be reversible and irreversible ways of handling the cancellations, where we discussed that can we reopen a closed class or we should only go with the existing classes in case of cancellations. And we discussed in detail that how you will have at the end of certain events available capacities in different classes using reversible and irreversible. We completed that exercise up to some of the events and then I asked all of you to complete the remaining table on your own, and I hope you would have completed that remaining table by using the discussion point for the reversible case as well as irreversible case. Moving further, whenever we are having such situation, you remember that we divided the total capacity in 4 different classes, and in the beginning itself we said that we are not going to take any booking in class 4. We had only class 1, class 2 and class 3 as the operating classes. Class 4 was closed. So, obvious question will come to your mind that how have we divided the available capacity in class 1, class 2, class 3, class 4 etc. It is very clear to all of us that our objective is maximization of total contribution coming from the booking systems. So, capacity allocation, that how much seats we are allocating for a particular class, how much we are allocating to a different class etc., that is a very important issue. So, before jumping directly for a multi-class capacity allocation, let us take a very specific and a simple case which is known as 2-class capacity allocation, because that is the simplest way of understanding that how capacities are allocated. And once we understand the 2-class model, we can extend this knowledge with some modification for a multi-class capacity allocation. And in that there are certain heuristics also which will help us in making our calculations much faster. So, in this particular session we are going to talk about a 2-class model. We will see that how we can handle that 2-class model using the decision tree approach. We will also talk about a very popular approach for solving such 2-class models which is known as Littlewood's approach. So, in most of the cases this Littlewood approach gives you maximized expected revenue from your booking systems. So, let us see the peculiarity of this 2-class model. As the name indicates, we are dividing the total capacity in 2 classes, A and B. For the sake of simplification and the meaning of these 2 classes, let us say class A is a discount class and class B is full fare class. So, the question is that if my system has a total capacity of let us say 100, how many of these 100 will go to discount class and how many of these will go to full fare class, that is the question. And let us see that 2-class model which is being developed on the basis of decision tree approach, what will be the solution coming for us. So, we are considering a low fare class which is I am calling as a discount class, and then this is high fare class which is I am calling as full fare. For discount class and full fare class, we are using the nomenclature as PD, discounted fare, PF, that is the full fare. So, PD and PF, these are the nomenclature we will be using in this entire session for representing our discounted class and full fare class. Now, discount customers each pay a fare PD, obviously PD is greater than 0, and full fare customer pays higher fare PF which is higher than PD. So, you can say that in the simple term, so that you can remember, PD is greater than 0 and PF is greater than PD. You can easily understand that if PF is equals to PD, if PF is equals to PD, then there is no meaning of two classes, then the entire system has only one class. So, PF has to be greater than PD. And generally one more important thing which we will be talking in detail, that in always these kind of systems, first you are exhausting all your discounted fare class capacity. Once your discounted fare class capacity is completed, is exhausted, then only full fare capacity is used. It is generally in these calculations considered that it is impossible that you still have a discounted fare class availability and you are booking in full fare class also. So, full fare will only come when discounted fares are over. So, these are the three important assumptions. We have limited number of seats, all discounted fare booking occur before full fare booking starts, and the incremental cost of carrying a passenger is 0. We will be talking in detail and we have already discussed the meaning of incremental cost in our earlier videos also. So, these are the three very important assumptions you should remember. Now, in this two class model, the important question which we are trying to address or we are trying to optimize, that how many discount bookings to allow or how many seats to reserve for full fare customers in order to maximize the revenue by deciding the discounted booking limits, or vice versa also. We have discussed the case of protection labels in our earlier classes also. So, the protection label for full fare class is the total capacity minus the booking limit for discounted class. For example, if you have the total capacity C equals to 100 and you are keeping, let us say, booking limit for discounted, that is 35. So, the protection label for high fare class, full fare class will be 100 minus 35 equals to 65. I request you, can you give me the answer that what will be the booking limit for full fare class in this case? Just think what will be the, with this example, with this data, what will be the booking limit for full fare class. We have discussed in our earlier classes also that what will be the booking limit for full fare class. Let me give you the answer that the booking limit for full fare class B full will be equals to the total capacity available for this system, that is 100. So, booking limit for the discount I have given, that is 35, and booking limit available for full fare will be 100 in this particular case. So, this is just refresh whatever we have learned in our previous classes. Now, in this particular case, how the model is going to be developed, and before that there are two very important terms which we will be telling you. These terms are, one is spoilage and another is dilution. You must have some idea by the name itself what is the meaning of spoilage and what is the meaning of dilution. Now, spoilage may occur because you may allow more seats, because you want more revenue. So, you can keep more seats for your full fare customers. Now, unfortunately, more full fare customers are not available. You kept a very high protection label for your full fare customers, enough full fare customers are not available, and when your flight took off, all those seats which remained unbooked will be lost. That is the lost inventory, lost capacity. So, that is the spoilage. So, you are not able to use your inventory because you kept a very high number of protection label for your full fare case. On the other side, now you become conservative, and in that conservative approach, more full fare customers will not be available. So, you are keeping a larger booking limit for your discounted fare class. Now, in this case it is quite possible that there were some customers available who are ready to pay full fare also, but you kept more seats for lower fare class, and in that way you are able to fulfill all your available inventory, but you have diluted your revenue, because the additional revenue was possible because more customers were willing to pay for full fare, but they paid lower fare, and therefore, the revenue maximization is diluted. You were expecting to collect, let us say 1000 rupees from that particular flight, but you actually collected only 800 or 700 rupees. So, you have diluted your total revenue by 200 300 rupees because of keeping more number of seats under the lower fare class. So, we actually want to avoid spoilage as well as dilution. I do not want spoilage, I do not want dilution. So, no spoilage, no dilution, because whether it is spoilage or dilution, both spoilage and dilution gives you suboptimal revenue, because in spoilage revenue is lost due to vacant seats. In dilution, revenue is lost because of lower collection, and you could have higher collection because of your excessive limits you are keeping for low fare class. So, please remember these two important terms whenever we are talking of capacity allocation. The trade off between spoilage and dilution, we do not want any one of them. So, here we if you have remembered that in one of our earlier sessions a few weeks before, we discussed that a very popular newsboy problem, and in that newsboy problem we discussed that what is the meaning of expected profit, expected cost, expected loss, etc., etc. So, we will borrow some of our discussion in today's class from that newsboy problem case. Here, to start our model, we are considering 3 types of probabilities. FD, D subscript is always related to discounted fare, and small f is always related to full fare. Now, FDX is probability for discounted demand being less than or equal to x. That discounted demand is x or less than x, and FFX is that probability that full fare demand being less than x. So, whatever is this x, that will be actually some numerics, and we are keeping these probabilities for full fare as well as discounted classes. Now, we are going to consider a popular way of handling such kind of probabilistic situations, and this is decision tree approach which we are going to apply in this particular case. In this decision tree, the situation is how much to allocate for discounted class and how much to allocate the full fare class. So, considering the case when the booking limit has been increased to B plus 1, you are keeping B for discount class, and now I am keeping it B plus 1, from B to B plus 1. If discount demand DD is less than or equal to B, there will be no effect on expected revenue. Therefore, net change in revenue is 0, shown in the topmost branch in the figure of this decision tree. So, you see that here we are keeping B to B plus 1, this particular part you can see in this available database, and B otherwise is keeping constant. So, 2 decisions are possible in the starting. I keep the booking limit for discounted class as B only, or I increase it to B plus 1. Now, when I am increasing to B plus 1, then there are 2 situations possible. like demand of the discounted fare is B, FDX. You remember we discussed that FDX is the probability that demand is X or less. So, now I am replacing this X with B here. So, it means that demand for discounted fare is less than or equals to B. So, if demand is less than or equals to B, by increasing the capacity to B plus 1, I am not able to use this additional capacity because the demand is only B. So, if I allocate more numbers in that category, there will be no benefit of that. So, the change in revenue relative impact is 0, there is no impact that is here. If FDB is there, so the other probability will be 1 minus FDB. That 1 minus FDB means that demand for discounted fare is more than B. Demand for discounted fare is less than B if probability is FDB. If the other possibility at this node is probability being 1 minus FDB, and if probability is 1 minus FDB, the demand of discounted fare class will be more than B. Now, if demand for discounted fare class is more than B, there are two possibilities. There are two possibilities that is further branched here. Now, 1 minus FFC minus B and FFC minus B. Now, C minus B is what? Can you recall what is this C minus B? C minus B is basically the protection label for high fare class. You recall that we discussed that this particular equation, protection label for full fare class is capacity minus the booking limit for discounted class. So, Y equals to C minus B. So, I am using this Y equals to C minus B for replacing this C minus B with that protection label, and this is. So, there are two possibilities that if demand is greater than B for a discounted class, either you are able to have the use of the protection label for your full fare class, that is the demand for full fare is less than or equals to Y, that is the protection label, or demand is more than, demand for full fare is more than the protection label, that is the upper part of this node. So, demand for full fare is more than protection label, this is easy to understand by this, and demand is for full fare is less than equals to protection label. Now, you please understand this point that when I am increasing the seats in my lower class, in discounted class, and the demand is more than that in the discounted class, now I have to see what is the impact of this higher demand in the lower class because of my available demand in the upper classes. Now, in the upper classes there are two possibilities. One possibility is that you are actually using it when the FF is demand for that is less than the protection label, and when the demand for full fare is less than for the protection label, you are going to get the impact in your revenue by PD, that is the additional seat in the lower class will give you one extra you can say revenue from that seat, that is the PD. But if demand in the upper class is more, if demand in the upper class is more than the protection label, then actually you are getting into this impact PD minus PF. PD is the discounted revenue and PF is the full revenue. So, in fact, you are eating the revenue of the full fare. You could have earned more revenue in the full fare, and now you are not getting that full fare revenue, and you can understand this is a situation. This is a situation we just discussed 2-3 minutes back. This is a situation of dilution, because you have reduced the capacity of the you have reduced the protection level of your full fare class, and you have allocated one more seat to the lower fare class, and there is a chance of more demand in the full fare class. So, the possible extra revenue which you could have earned in your higher class, that is sacrificed, and that is the situation of dilution. And obviously, so these are the 3 branches we discussed, and the 4th branch, that is we are keeping the B constant. B is constant. So, if there is no change in the capacity allocation, so there is no relative impact. So, there are out of 2, there are 2 situations where you are having no impact. There is one situation where you are leading to dilution of your revenue. That is how you can understand this entire decision tree model. Let us see further. Now, when you are having the discounted demand more than the capacity B, and if DF, the full fare demand, is more than this protection level C minus B, then the loss due to dilution is DF minus DD. But if the demand for full fare is less than this protection level, then the revenue will increase by PD, as that seat would have been vacant otherwise. So, you have actually minimized the scope of going into the spoilage situation, because of utilizing that capacity which is going unfulfilled in the higher fare class. You have actually taken the benefit of that. So, depending upon whether you are having more demand in the higher fare class or lesser demand in the higher fare class, you can take a call, should we go for increasing the capacity in the lower fare or not. But it is not so easy to know. We will use the Littlewood rule for that purpose. The expected change in revenue from changing the booking limit from B to B plus 1 is the probability weighted sum of the possible outcomes. So, possible outcomes are 1, 2, 3 and 4. These are the 4 important outcomes we just discussed, and out of these 4, these 3 are when we increase B to B plus 1. The fourth outcome is the result when we are not changing the capacity to anything. Now, using this entire knowledge, our expected revenue increase is the weighted sum of all these 3 things. So, all these 3 possibilities are coming because of some probability, that the probability is this probability is leading to this, then this multiplied by this leading to this multiplied by this probability is leading to this. So, this has to be a weighted sum of these 3 possible outcomes, which can be written in a very simpler form. In this is that weighted sum of 3 possibilities, 3 outcomes which are going to happen. The right hand side of this equation is greater than 0, then it is profitable to increase the booking limit to B plus 1. So, the point is that, as we discussed few minutes back, this is 0. Okay. So, 0 multiplied by FD into B will be 0 always. Now, this PD minus PF, you see that this has to be negative. We always will have this negative, because you may remember in the beginning of this session we said that PF is greater than PD. So, since PF is greater than PD, so PD minus PF will be negative, and PD is going to be a positive number. So, out of these three outcomes, one is 0 which will not give any impact, one is negative and one is positive. So, therefore, it is quite possible that this right hand expression in this equation 1 may be sometime negative, may be sometime positive. But when it is positive, and that negative positive depends on two things. One is the relative difference between PD and PF, that is going to tell you that how much negative is the second outcome, and second is it will also be depending upon the relative probabilities, that what is these probabilities, because this 1 minus f d into b, that is common to both these factors. So, what is the full fair protection level probability and 1 minus of that. So, on that relative term this expression will depend 1 minus f d into b, and this is the term which is common, and then based on this term you will decide that whether this expression is positive or negative. But if it is positive, then you should increase your capacity from B to B plus 1, and in this expression you can see that whether it is going to be positive or negative, it is basically dependent. This is the expression which is actually governing the positive or negative aspect, and therefore, this C minus B, which we have already discussed as a protection label, and 1 minus is the probability of the full fare booking being more than y, and for solving this particular equation there comes a very interesting rule, that is Littlewood rule, because 1 minus f f C minus B, one scientist around 1970s, he gave this system that 1 minus f f C minus B to decide what should be the booking limit for your lower fare class should be equal to P d upon P f, and this ratio of discounted fare and full fare is the deciding factor basically for deciding the limits for your discounted fare. So, 1 minus f f C y, which is 1 minus f f protection label, equals to P d upon P f. So, P d upon P f is basically deciding the booking limit. Take one or two very extreme cases. For example, take one case where P d is equals to 0. Now, P d is 0 means discounted fare is 0, you are not charging anything to discounted fare. So, what does it indicate? It indicates that full fare protection label, full fare protection label is equals to 1. That means there is no need for keeping any capacity for the discounted class, because discounted class is not giving any addition for your revenue. So, therefore, you can keep the entire class, entire capacity for your full fare customers. And you can take another situation, this will give you that if P d equals to P f, now you are increasing your discounted fare, the initial discounted fare is 0 and now you start increasing your discounted fare. So, there will come a situation where P d equals to P f, and if P d equals to P f, then it will signify that you should not have any protection label, you should not have any protection label for your full fare class. That means, full fare and discounted fare all are same. So, the entire capacity can be given on the discounted fare class itself. So, these are the two extreme cases. In one case and in fact, both these cases are resulting that you are not going to divide your capacity into classes, you are going to have only one class in your server, whether it is you can call that either low class or higher class, but there will be only one class if you have either P d equals to 0 or you have PD equals to PF. So, that becomes a very simple way of identifying that how much capacity you are going to have. So, this Littlewood rule which actually comes from this entire decision tree model, but it becomes very simple to actually execute with the help of this Littlewood rule, and we will continue with this Littlewood rules more example in our next class. With this we actually come to end of this particular session. Thank you very much.